Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to Learn Mathematics. And in today's video, we are going to discuss here the third part of our double integral video series that deals with your Fubini Theorem of iterated integration over non-rectangular regions or general regions like that. So here Vito Ubini, an Italian mathematician that we discuss in the part 2 of our videos, he presented here two methods of iterated integration, how to perform iterated integration over non-rectangular or irregular regions. The first one is said to be the vertically simple method, another one is horizontally simple method. So first of all, we just move on to the vertically simple method and let's see how it is geometrically, and then we just try to look at an example relative to it. Okay, so let's see the vertically simple method. So here it is. I just tried to draw here a rectangular region G first of all, that is bounded by A and B values on the x-axis and C and D by on the y-axis. So this is my plane G, which is rectangular entirely, and within this G I just tried to draw an irregular region which is lying inside your G, and I call it D, and it is bounded by the two curves representing two functions and the two lines which are x equals to B and x equals to A. So this region that is associated here with the graphite, it is bounded by these two lines and these two curves. Okay, and our objective is to find out, number one, the area of this region, and number two, the volume occupied by the object which is bounded by this plane D, irregular plane D, and the surface which is going to be right above towards it in the 3D space. So we'll try to manage the figure related to the surface and this plane, the figure of that object later on at the end of this lecture. But first of all, we just try to understand how we just obtain the area of this shaded region with the help of iterated integration through vertically simple. So in vertically simple, what we do, we just fix our x value over here. Okay, and in other words, you can say that we are going to concentrate on the number values of our x, which is bounded by this closed interval AB. Okay, and we can observe here that for each fixed value of x, there corresponds the values of y that lies between these two curves. Okay, like for example, if I say that I'm having here this point and it is having x coordinate as x1, and I just call this point as x1. So if I talk about this point, it is having x coordinate x1, and the y coordinate is lying on this curve, so it is equal to your h1x. I just call this curve as h1x. So this is it. And in the same way, if I talk about this point, it is having the same x coordinate, you can see x1, and the y coordinate is lying right above this h1x, so it is greater than h1x, and I just call it y2. You keep on moving like this. The x1 values are fixed here and the y1 values are varying, and they are restricted between these two curves. Similarly, when you move on to this point is having the same x1 coordinate, just like this, and the y coordinate is lying on this curve, so it is equals to your h2x. We can observe that for each x1, you are having a range of your y values which are bounded by these two curves. So you can observe like this, that for all values of x, there exist the values of y which lie between these two curves. Okay, so this is the range in which this y is bounded. Alright, so this is it. So in the same way, you are having infinite such points. So how we obtain here the area? So like that, if I just assume, I just try to manage here a simple way of understanding. So I just say that this is a piece of stick, if the stick starts moving from this x equals to a, okay, and is restricted between these two curves, h1x and h2x, and it keeps on moving, and with respect to the two curves width, this stick is trying to manage its length, okay. So it is like this, it's constantly moving, and then it's restricted like this, and then it's moving, and towards, once when it reached a value of x equals to b, it stops. That's how it covers this entire area, okay. So if you cover all the values of y from this point to this point, from this curve to this curve, and all the values of x from a to b, we are going to obtain this entire area, okay. So here in vertically simple region, in the vertically simple method, for all value of x belonging to this interval AB, there exists a value of y which belong to this range, where h1x and h2x are the functions which are representing these curves, okay. So what we do exactly, if the integrand that is provided to us, if it is a well-defined algebraic expression, then if we try to integrate this with respect to y first, keeping these as our integral limits, we are going to get some function, and that is going to be the integrand for this integral that we are going to integrate with respect to x, bounded by these limits, okay. And once when we finish this entire stuff, we are going to get the volume of the object bounded by this plane and the surface right above to it, okay. And if for example, if the integrand is equals to 1, if it is a unit integrand, then in that case, once when you perform this double integration, whatever the answer you get, that answer is going to reveal the area bounded by this plane D, and that's it. No volume is there. So that's what your vertically simple method say. That in vertically simple method, what you do, you first integrate your integrand with respect to y, and then with respect to x, okay. Here x limits are in the number form, and the y limits, integral limits, are in the form of algebraic expressions involving the variable x. So that's it. In the same manner, let's move on to the horizontally simple method. So for that purpose, I have to just drag my page right above. So this is it. Okay, now that's enough. Alright. So in horizontally simple method, what we do, we are having the same plane, rectangular plane G, and within the plane I have managed here another irregular region D, bounded by these two curves and these two lines, y is equals to c, y is equals to d, okay. And these curves, I'm going to represent them in this way. Here this time my x is going to be my dependent variable and y is behaving as an independent variable. So function is going to be expressed in terms of y here, okay. So this curve is representing h1y, and this curve is represented as h2y function, alright. So here in horizontally simple method, what we do, we are going to fix the value of y, okay. So just like what we did in the vertically simple, I just tried to manage here a line segment which is originated at from this point, okay. For every fixed value of y this time, there is going to be a range of your x coordinates which are going to be bounded between these two curves, okay. So for example, if I just pick up this point is having its y coordinate y1. I just name this as y1 for my convenience, and this point is going to it is lying on your h1y curve, so it is going to be, the x coordinate is going to be expressed as your h1y. Let me write it much more clearly over here. So this h1y is the x coordinate, and this is said to be your y coordinate, okay. I think this is much visible. So that's it. This is said to be your h1y coordinate. You keep on moving. If you come over here, then it is also having the same y1 coordinate, and x coordinate is right ahead of this one, so it is greater, it is having the value greater than this one. So this is your x2. You keep on moving till you achieve over here, you reach over here. So this is the point which is also having the same y1 coordinate, and the x coordinate is lying on this curve, so it is going to be traced right over here, represented as h2y. So this is the h2y x coordinate, and this is your y1. So you see, for each fixed value of y, you are going to have a range of your x coordinates bounded between these two curves. Okay, so that's what we just I just tried to write over here, that for all values of y belonging to this closed interval CD, there exists a range of your x values which is resting within this range. Okay, this is less than equals to, the ink just got split up, so this is it. Okay, so how you manage the area? If you just manage a stick over here and you are moving from C to D, and the stick is restricted between these two curves, it is going to manage its length with respect to the wideness of this region. Like if it is moving from C, y is equals to C, and restricted between h1y and h2y curves, it is moving like this. Okay, it is moving like this till it achieves y is equals to D here. So that's how it covers the entire area of this irregular region D. Okay, so how you do? In horizontally simple method, you are going to integrate your integrand with respect to x first, bounded by these two limits. Okay, you're going to get some answer in form of algebraic function. Okay, and that function is going to behave as an integrand for this integral that you are going to integrate with respect to y, keeping these integral limits. Okay, so whatever you got, that is going to be the volume of the object bounded by this plane D and the surface right above to it. And the surface right above to it is going to be sketched by the help of your xy coordinates bounded by these values, and the y coordinate is going to be interpreted by this function. Alright, so that's how you do. This is the value of the volume, and if you're having f of xy equals to 1, then this integral, double integral, is going to give you nothing but the area of this plane D, and that's it. Okay, so this is just a rough sketch that I tried to manage. The more precise one will be at the end of this lecture. So this is, for example, if this is the plane D, and this is some surface that is expressed by this function x and y and z is this function, is revealed by means of this function. And if I just say that f of xy is expressed by this expression, then z can be evaluated by means of this expression over here. So once when it is sketched in a 3D coordinate system, it is going to give you a shape, for example, like this. And if you just try to maintain an image or a shadow of this plane right over there, and you are having some region over here, and if you bound an object between these two surfaces, that volume is going to be evaluated either by this method or by this method. Alright, let's move ahead to the examples now. Okay, so this is your example that we are going to integrate this integrand, which is your f of xy actually, and over here and the region that is so given to us is bounded by these two functions. This is the straight line, this is a parabolic curve. So first of all, what we do in order to get the volume bounded by the surface and this plane D, we have to sketch a figure first. Okay, once when we sketch the figure, then we are going to apply both the methods, vertically simple and horizontally simple, to get the volume. Alright, and both methods are going to give you the same answer. So here this is the horizontally simple method, and first of all we are going to sketch here the graph in order to understand how what exactly the appearance of this plane D going to be. So here for this equation, for this function, I just try to manage here few points. Okay, so this is it. For x equals to 0, the y is also 0, and if you put x either positive half or negative half, in both cases you're going to have the same value of y, which is 1 upon 4. These are the 2 points that I just wrote in a single ordered pair form. And in the same way, if you just put positive or negative 1, in both cases you're going to have the same value of y, which is 1. Alright, so these are the couple of points that I'm going to plot related to this function. And as far as this function is concerned, it's quite easy going. Whatever the value of x you are going to get, the same value is going to be for the y. So this is a reflex so this is something that you call a linear equation. Alright, a straight line we are going to get here with the y-intercept at the origin, so on. The slope is 1. So once when we try to plot these points on a graph paper, on a 2D coordinate system, it looks something like this. You can see the curve here. This is the parabolic curve, and representing this equation y is equals to x squared, and this is your straight line representing y equals to x. So the intersection of these two functions that you can observe here is this region, which is shaded with the graphite. Okay, this is it. As far as the points of intersections are concerned, you can do it algebraically, and also you can analyze it geometrically. So this point is 1, 1, and this point is at the origin, so it is 0, 0. So algebraically we can obtain it like this, that if you compare these two equations, both are y equals to x and y equals to x squared. So if you compare these two expressions written at the right side, it looks like this. Okay, and once when you try to solve it by switching your x over here and then taking out one x common, you're going to have two factors here. So both factors you're going to equate equals to 0. It looks like this, and in this way you are going to have the two answers of your x. This is a quadratic equation, so going to give you two values of x as a solution. And once when you substitute these two values of x either in this equation or in this, you're going to get the corresponding value of your y. So I just selected here the simple equation, linear equation y equals to x. When I substitute x0 here, I'm having y0. When I substitute x1 here, I put the y value of 1. So the point of intersections that you can observe here are 0, 0, and 1, 1. Same, it is visible geometrically as well. Okay, so this is exactly the regions are. Okay, now I am trying to do this double integration by vertically simple method. So I'm going to keep my x fixed here. So this is going to be my stick. And this stick is moving from this curve to this curve, so it is restricted between y equals to x squared and y equals to 1. So it is actually moving something like this. From x0 to x1, it is going to move something like this. Okay, so how it is moving this with respect to the y activity, its progress is from this curve to this line. So this curve is going to behave as the lower limit of my y integral, and this is going to be this equation is going to behave as the upper limit of my y integral. Okay, so that's how it is going to be, that for all values of x moving from 0 to 1, there exists the value of y lying within this range. Okay, so these are my integral limits. Let us now try to integrate it through vertically simple method. So here how we are going to organize our double integral. This is your f of x y, alright, and we are going to integrate with respect to y first, keeping these limits, the lower and the upper, as we have discussed. So you can see here we are going to integrate with respect to y, and we are having x squared here. So as we know that in vertically simple method we keep x fixed, that is, we keep the x constant. So once x is behaving as a constant here, so we are going to write it outside this integral, and it looks something like this. Now we are having integrand 1 here, so we are going to integrate it with respect to y. We are having something like this. Okay, and then we are going to apply the limits here on y, the upper first, then we are going to subtract it with the lower. So it looks something like this after applying the integral limits of your y. You're going to multiply this with these two terms. You're having an appearance like this. My writing is too bad. This is actually your cubic power. Okay, that's the cubic power. Now we are going to integrate these two terms individually like this. We are going to apply here the formula of xn, which is x power n plus 1 upon n plus 1. So we just applied it, and this is it. It appears something like this. Then you apply your integral, and then you take the LCM, and finally you got this answer. This is the volume bounded by that plane D and the surface right above to it. So the object so bounded by that plane D and the surface right above to it is going to occupy this much volume. Now in the same way, we are going to approach to the horizontally simple method, and before approaching to horizontally simple method, let's try to see its corresponding graph activity. Okay, you can see here, this is the plane D, and this time we are going to keep our y fixed. So this is going to be the strip or the stick right parallel to your x-axis, and this strip is moving from 0 to 1. It is going to travel like this. Okay, it is going to travel something like this from this point to this point, something like this. Okay, so it is moving parallel to your x-axis from 0 to 1 on the y-axis. Okay, so the limits of your y integral are going to be from 0 to 1, and that of your x integral are going to be from y equals to x, or in other words x equals to y, which is this. Okay, and moving towards this curve, so this curve is going to be interpreted as your x equals to under root y, because we have to express our function with respect to y. Y is the independent variable here, so we just try to modify our equation keeping x as a subject. Okay, so this is going to be the limits for all the values of y from 0 to 1. There corresponds the value of x, which is lying within this range, expressed like this. So these are the integral limits with respect to x, and this is the integral limits with respect to y. So let us now try to integrate it with the horizontally simple method. So that's how this time we are going to express our integration. We are going to integrate first with respect to x. This time this is a very definite integrand. We are not going to take it as a constant, obviously, because we are integrating with respect to x, and this is an expression involving x here. So we just apply here the basic integral formula, and then we are going to apply the limits on this variable x cubed. 1 upon 3 is a constant number written outside the integral. It looks like this, and then we apply here our limits. So y power half, the upper limit is applied first, subtraction, lower limit afterwards. We just solve it like this, and then we are going to take our we are going to apply the integration individually on these two terms. Alright, that's it. Now we are going to apply here the formula of your x power n, which is x power n plus 1 upon n plus 1. So that's how it appears to be. Okay, 3 by 2 plus 1 give you 5 by 2, and so forth. But this is it. Now we are going to apply here the limits. So once the limits are just 0 and 1, so no matter what power comes on the 1 remains 1. And same thing happens with the 0, so it looks something like this. Okay, and then you just take out your LCM over here. The LCM gives you something this, which is 3 by 20 multiplied by 1 by 3. On solving, you're going to have the same answer. You can see what we got right over here. So that's it. The horizontally simple and the vertically simple methods are helping you to sort out your volume, and that's it. So let us see what could be the shape of the object whose volume is this. Okay, so this is the surface that I tried to sketch here. this blue thing, a curved paper type thing. So this is it looks like a trough or what. So this is the surface, which is so interpreted by means of in this way. Here your z coordinate can be obtained with the help of this function, and our function is x squared here. So once when you try to plot this function on the x coordinate on the 3D coordinate system, we are going to have a surface having this shape, okay? And right over this surface, the plane on the xy plane, okay, I just manage here the curve y is equals to x squared and the line y is equals to x, so it gives me an intersection region D here. So the shadow or the image of this cross-sectional plane that is lying right over this surface is occupying this much region on the surface. So this region and this region, I'm going to bound an object right between these two, right between this surface portion and this plane D. So whatever the object that I got, it is having a shape something like this as far as I try to sketch. So the volume of this 3D object is 1 upon 20. So let us try to have a look on 3D graph software. So that's my Runiter 3D graphic calculator, and this is the equation that I just tried to maintain. Z is equals to x squared. So it is exactly sketching the same surface. You can see it looks something like this. Okay, and that's what I tried to plot on that piece of paper. And that's another software that gives me the same region D here. This is your x equals x, y is equals to x squared. This is your y is equals to x. So the intersection region is D is right over here, having the same intersection point 0, 0 and 1, 1. Okay, so I just tried to lock here, and I just tried to pick up only this intersection region. It gives me stuff. It gives me something like this. You can see this was the region, and when I just tried to manage its 3D image, how exactly it looks like, it gives me an object having this shape, and there are several. It is interpreted by several rectangles. You can see, right? So the individual volumes of all these rectangles, when we try to sum them up, it gives me the volume of this entire 3D object, right? So that's what exactly the iterated double integral helps us to evaluate. Okay. So that's all for today. And if you find this video helpful, I humbly request you to subscribe my channel and put down your feedbacks in the comment box below, and try to share this video as much as you can. And if you find do give me a positive or negative, both kind of feedbacks, whatever you find, in order to improve the quality of the videos and the nature of the lectures and all that. So I'll see you soon with the next video with some nice topic, maybe the volume of the solids obtained by the revolutions on a certain axis and all that. So take good care of yourself. I'll see you soon. Allah Hafiz.